On behalf of 24HourAnswers.com, I welcome you to today's lesson. In this video, we're going to take the calculus approach to finding the intervals of increasing and decreasing of f of x, and we're also going to determine the location of any maxima or minima. Now, the calculus approach is a bit different than the algebraic approach. If you have not watched part 1, I encourage you to check that out, where I go over some of the basic algebraic steps to do the same thing that we're going to do here. However, algebra is very limited when we start messing with other functions such as cubic functions, quartic functions, trigonometric functions, logarithms, and things like that. So we want to know the calculus, and I'm still going to stick to a basic parabola to get this idea across to you. Now, back in the algebraic part 1 video, we discussed that this was a parabola that opens up because the leading coefficient is positive. We're guaranteed to have a minimum here, and we actually have an absolute minimum. Not only that, if you think back to your college algebra days, we know the function is going to be decreasing on the left side and increasing on the right-hand side. Again, the algebra is limited when you start messing with other functions. So let's take the calculus approach, and we can apply this to other functions later on in further tutorials. Let's find the derivative of f of x. F prime of x is going to be 2x plus 6, just using your basic differentiation rules. We want to find what's called critical values. Critical values are when the derivative is equal to 0 or when the derivative is undefined. Now, this derivative, 2x plus 6, is defined for all x, so the only thing we have to worry about is when the derivative is equal to 0. So setting the derivative equal to 0, subtracting 6 from both sides, and then finally dividing by 2, we have a critical value of -3. This is where our derivative may change signs. In this case, it is going to change signs, but it doesn't always do that. So I'm taking that critical value of -3 and I'm putting it on a number line. I'm going to make up some test values, TV, just some test values. I'm going to pick one number that's on the left side of -3, such as -4. That test value is just fine. And let's pick a number on the right side of -3. You could pick -2, you could pick -1. I'm going to pick 0. It does not matter. This is the only critical value we have for this function. Now we are curious about the sign of the derivative, sign of f prime of x, at these test values. So let's take these test values, let's plug them into the derivative, and all we care about is the sign. Is it positive or is it negative? Let's test out -4. 2 times -4 is -8, plus 6 gives us -2. So all I care about is the fact that the derivative, when x is -4, it is a negative derivative. If the derivative is negative, the function is decreasing. That tells me right off the bat that the function is decreasing on the left side of -3. What about on the right side of -3? Let's test our derivative at this test value of 0. 2 times 0 is 0, plus 6 gives us a positive 6. So when we plug in any number to the right of -3, I just tested 0, you will get a positive number for your derivative, which implies if the derivative is positive, the function is increasing. So we already have our spots where our function is decreasing and increasing. The function is decreasing on the left side of -3, hence this part right here. Notice as I move my pen from left to right, my pen is going down. Hence, we have a decreasing spot. On the right side of -3, that's going to be this spot right here. As we move our pen from left to right, it's going to go up on this curve. Hence, we have our increasing interval. To write these intervals in interval notation, we would say all values of x from -infinity to -3, our function is decreasing from -infinity to -3. These are values of x. Our function is increasing from values of x that go from -3 and forever to the right. We're going forever to the right, so that's to positive infinity. This is our interval of increase. We always use values of x when we talk about intervals of decreasing or increasing. And just, if it helps, throw your positive and negative infinity up here to help you determine, which one goes where. As we go forever to the left, that's negative infinity. Forever to the right, that's positive infinity. Now, what about our maxima and minima? Well, this function, this parabola, which is a rough sketch of this parabola, If our function goes from decreasing to increasing, you're guaranteed to have a minimum. Is it an absolute minimum? Well, you may need to do more calculus to determine that, but since this is a parabola, we're guaranteed to have an absolute minimum at this point. Well, what is that minimum? To determine that, we actually take the -3. We don't plug it into the derivative. That's going to give you 0. You want to take -3 and plug it into the original function, which was x squared plus 6x, and I'm plugging my -3 in, and then it was plus 2, I believe. Let's double check that. Yes. And working all this out, we have 9 minus 18. That's -9 plus 2. We get -7. So we have a minimum of -7 when x is equal to -3. Our ordered pair there will be -3, -7. So let's look back at what we've done all this together. We have found the intervals of increasing and decreasing right here. And one thing to note here, I did not put brackets around these because the function is not decreasing nor is it increasing at exactly x equal to -3, because that's where the derivative is actually equal to 0 based on our critical values. Then we also came and found the actual minima. We didn't have a maximum in this problem, and we determined that by using the critical value, plugging it back into the original function. Make sure you remember that. And then we can also go over to Desmos or any graphing calculator app, and you can look at the original function here, f of x equals x squared plus 6x plus 2. Notice from values of x from -infinity all the way to this x value of -3, which is right there, the function is decreasing. And then from -3 on to +infinity for values of x, the function starts to increase again. And again, visually, look, if we go from decreasing to increasing, we have a minimum. Now again, this is a very basic example because this is a quadratic. This is a parabola. When we start looking at logarithms, trigonometric functions, and higher order polynomials, that's where the calculus is going to be your best bet, because you can't really do a lot of algebra to determine that unless you had a graphing calculator. But a lot of this stuff is going to be done pencil and paper, and we can use a graphing app to check our work. And there you have it, intervals of increasing and decreasing, a very basic example here of a parabola. This is the part 2. If you have not checked out part 1, this is a good review of looking back at how you used to do this stuff with the parabola. But again, now we have some calculus techniques that will take us much further and help us deal with much tougher functions. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.